Hello guys, here I am going to explain some concepts that is required for your competitive examination regarding the regulation of gene expression. So only for NEET students, the board as well as this one, GAEE students, no need to watch this video. Okay, so we write the diagram. Okay, so of lac operon, piposia. Okay, so we just put them in the box so it will be easy for us to know. Okay, so this I, the regulatory gene, here in the lac operon concept, I in the sense it is inhibitor. It's going to inhibit the transcription of ZYA, that is the structural genes. We write here structural genes. Okay, if you take tryptophan operon concept, I in the sense inducer. So it's going to switch on the ZYA gene, that is the product of I gene or regulatory gene. So it is entirely different. Okay, so we just write the mRNA, which is also called as repressor mRNA, which is going to get translated to produce so we just mark this, that is repressor protein, rep protein. Okay. So the production of rep protein is 24/7. So I have already informed that it is also called as constitutive genes. Okay, so constitutive gene is nothing but regulatory gene, that is I gene. Okay, so let me write here. Okay, so we will write lac operon is also called as inducible system. Why lac operon is called as inducible system? Because the lac operon, that is ZYA genes, which get switched on only when lactose is present. So we just put the dots here. This is now lactose. So increasing the concentration of the lactose will turn on ZYA genes. That is mainly when the lactose should block the repressor protein from binding to the operator site of the structural gene. So let us imagine that this is now the lactose. Even the allolactose also acts like inducer. Lactose or allolactose both can act as inducer, which will bind to the repressor protein. So lactose is the chemical. It is a disaccharide which has to get metabolized to synthesize ATP within the E. coli, which itself acts like the inducer. So lac operon is a very good example for inducible system. Why? Because lactose is itself. Because lactose has kind of two functions. One is it is going to switch on the structural genes by blocking the repressor protein, number one. Second thing is it is the metabolic chemical which is going to produce the ATP in the absence of glucose. So it is the inducible system. Okay, so that's it. Next I am going to write one more thing, that lac operon is a very good example for negative feedback system. So if you take the gene regulation, lac operon is negative feedback. Okay. What is this negative feedback? Negative feedback means in the absence of the lactose, that is the second metabolite. Okay, not secondary metabolite, it is the second metabolite. The first one is glucose. In the absence of lactose, let us imagine there is no lactose. So what's going to happen is, I do not want these ZYA gene to be activated, so I need to block it. So this one, the constitutive gene, the gene I, is going to produce the repressor protein, and this protein is going to bind to the operator and blocks the path of RNA polymerase. That's it. So ZYA cannot produce the respective enzymes in the absence of lactose. Got it? So it is negative feedback. The repressor itself going to bind to the operator site, so it is negative feedback. Okay. Now I can also make this as the lac operon as positive feedback. I can make it. Okay, naturally it is a negative feedback mechanism, that is lac operon, but I can convert it into positive feedback. How? See, let us just imagine that okay, so the entire board has the cytoplasm of the E. coli, and what we have is here, we have glucose. We have glucose here. The percentage of the glucose is now 90. So 90% is glucose. Okay, so it is understood that when glucose percentage is high, the entire lac operon is switched off. ZYA is not working, inactive. And the percentage of lactose is 10, so 10% lactose. Compared to glucose, the percentage of lactose is very less. So now lactose is there, right? At least 10% is there. So I need a ZYA gene to synthesize synthesize the enzymes to break or hydrolyze this lactose to produce ATP. At the same time, I need the ZYA, that is lac operon genes, structural genes, should be in off mode because glucose is present. So I demand two conditions. One is I need ZYA gene to be switched off. At the same time, I need ZYA genes to be switched on. See, I am demanding two conditions because both are present, but the concentration is different. Yes? Okay. So when the glucose concentration is very high, obviously this one, what you call the repressor protein, is going to bind to this. That is it. At the same time, the lactose percentage is bit less, but it is enough to bind to the repressor protein. So that means actually, there will be not a continuous what you call switch off, switch on mechanism will take place. Like what we say, like in the 24 hours. Like that we say, like first 10 minutes lac operon will be switched off, next 10 minutes operon is switched on, next 10 minutes off. So you see that alternating, switch on, switch off, switch on, switch off. Got it? Because we have both. Got it? Okay. Now I want this entire lac operon to be in the positive. It's like positive feedback. What is positive feedback? Okay. So now let us just imagine that glucose, earlier it was 90% because of the activation of another gene. I'm not talking about this gene, which will metabolize the glucose. So to synthesize ATP, that is through glycolysis pathway, the concentration is now reduced because all the glucose is converted into pyruvic acid to produce the ATP. So glucose concentration is coming down. Okay. Now let us imagine that in the outside medium, the glucose is not available. Only lactose is available. So I said this enzyme, ZYA enzyme, which is not that active, like it's like inactive, but still it can produce beta galactosidase, permease, and the last one, the trans-acetylase enzyme in small amounts because lactose is present, that is 10%. Okay, but still we say like it is switched off, but still it can produce in small amounts. Okay, this is very important. Okay, so don't get confused with that. That means like when I say switched off, it's everything is switched off. No, it will be in active state. Okay, at least for some time because lactose is present. That means you cannot see E. coli without lactose. That means at least 1% lactose will be there within the cytoplasm of the E. coli. But glucose, they give more preference to glucose because that is the main metabolite for them to synthesize ATP. Okay, so let us now imagine as the concentration of the glucose is getting down, it has to make a arrangement to survive. That is actually they have to take the food, available food. Let us imagine lactose is outside, more lactose is outside. So it's going to take, how it is going to take? Because as I said, like the structural gene will be active in some time. Okay, so this permease enzyme will be synthesized. That's going to bind to the plasma membrane and acts like a transmembrane protein, and which will allow this lactose to get inside. So what's going to happen? More lactose get inside the cytoplasm, the concentration now increases to 90%. Okay, so I need somebody to activate ZYA genes, structural genes. Earlier it's like now getting activated. Okay, so it's like almost like activated because the lactose will go and bind to the repressor protein. But the speed of synthesis of beta galactosidase, permease, trans-acetylase is not enough to hydrolyze all the 90% lactose because the percentage is very high. It's like more in number. So I need to increase the rate of synthesis of these enzymes from these genes. How can I increase it? So I need to ask someone to bind to the particularly like promoter site and asking more RNA polymerase to come and bind to the promoter so that it can read ZYA in much faster way. Okay, so as a result, more and more enzymes will be synthesized. This is very important. So that is called as positive feedback. How positive feedback works? When the concentration of the glucose goes down, is going down, the reducing in the concentration in the cytoplasm, that is glucose concentration. What's going to happen? There is one activation mechanism takes place. Activation of cyclic AMP. What is cyclic AMP? Cyclic AMP is nothing but second messenger. Remember this. Even I had explained about cyclic AMP in the previous year when I was discussing about mechanism of hormone action. Cyclic AMP, which is a second messenger, it will detect the reducing concentration of the glucose, and the concentration of cyclic AMP increases. When the concentration of the cyclic AMP increases, there are so many mechanisms occur. Let me just shorten it. It attracts one protein called as cyclic AMP receptor protein. Okay, it will attract cyclic AMP receptor protein, which will bind to cyclic AMP, makes it a complex, that is cyclic AMP receptor complex. So two things now are bound. Okay, so this is now cyclic AMP, this is now CRP. So they are going to bind, making it a complex. This complex will go and bind to the promoter of the structural gene. Okay, so which now it's bound to the promoter, which attracts the RNA polymerase to come and bind to the promoter, and as a result they read ZYA genes, structural genes, in a faster way compared to the earlier state. Got it? As a result, the concentration of, or the rate of synthesis of all these enzymes from the structural gene increases. That is maybe 10x fold. Got it? It's rapid compared to earlier stage. This is positive feedback. Got it? So this is the thing. Hope you understood what is inducible system, negative feedback and positive feedback. Okay. Now I'll erase it and I'll go with one more concept, that is tryptophan operon. Okay. So let me erase it and I think I'll take one more session.